many cases, house heating, ventilation, and air conditioning ducts are grounded. The National Electrical Code in the United States requires that all exposed metal surfaces, including heating, ventilation, and air conditioning ducts, be grounded for safety reasons to prevent electrical shocks. The International Building Code also requires heating, ventilation, and air conditioning ducts to be connected to the grounding system. Heating, ventilation, and air conditioning ducts are typically grounded through one of the following methods. Firstly, direct bonding, where the ducts are directly connected to a grounding electrode, such as a ground rod or water pipe. Secondly, equipment grounding conductor, where the ducts are connected to the equipment grounding conductor that runs through the electrical system. This conductor connects the furnace or air handler to the electrical panel. Thirdly, metal support straps, where the ducts may be indirectly grounded through metal support straps that are connected to a grounded structure, such as the furnace or the house frame. Grounding heating, ventilation, and air conditioning ducts provides several benefits. Firstly, safety by preventing electrical shocks by providing a path for electrical currents to safely discharge. Secondly, static discharge, where grounding dissipates static electricity that can accumulate in the ducts due to friction with air and dust. Thirdly, electromagnetic interference reduction, where grounding helps to reduce electromagnetic interference by providing a low resistance path for electrical noise to flow through. In some cases, heating, ventilation, and air conditioning ducts may not be required to be grounded in situations such as ducts made of non-metallic materials, such as plastic or fiberglass, or ducts that are completely insulated and not exposed to any conductive surfaces. While grounded heating, ventilation, and air conditioning ducts are important for safety, homeowners should not attempt to ground them themselves. This should be done by a qualified electrician who can ensure that the grounding is properly installed and meets all applicable codes and standards. It's important to understand the reasons why grounding is crucial in HVAC systems. Grounding provides a low resistance path for fault currents, minimizing the risk of electrical shock. Static electricity buildup in ducts can attract dust and other particles, potentially affecting air quality and system performance. Grounding can help to dissipate the static charge. Electrical noise from various sources can interfere with sensitive electronic equipment. Grounding provides a path for this noise to flow to ground, reducing its impact. It is crucial for heating, ventilation, and air conditioning systems to meet the requirements outlined in the National Electrical Code and International Building Code. These codes establish minimum safety standards for electrical installations, including grounding of metal components. Adhering to these codes helps ensure the safe and reliable operation of heating, ventilation, and air conditioning systems. Several methods are available for grounding heating, ventilation, and air conditioning ducts, each with its own advantages and disadvantages. Direct bonding involves connecting the ductwork directly to a grounding electrode, such as a ground rod or water pipe. This method provides a low impedance ground path and is often preferred for its effectiveness. The equipment grounding conductor, or EC, runs from the electrical panel to the heating, ventilation, and air conditioning equipment. Connecting the ductwork to the EGC provides a ground path through the electrical system. Metal support straps can provide an indirect ground path if they are connected to a grounded structure such as the building frame or the furnace. However, this method may not be as effective as direct bonding or connection to the EGC. When grounding heating, ventilation, and air conditioning ducts, consider the following factors. Firstly, ensure that the grounding conductors are properly sized and installed according to code requirements. Secondly, make sure that all connections are clean and tight to minimize resistance. Thirdly, inspect the grounding system regularly to ensure its integrity. While grounding offers numerous benefits, exceptions may exist in certain situations. Non-metallic ducts, such as those made of plastic or fiberglass, do not require grounding since they are not conductive. Fully insulated ducts that are not exposed to any conductive surfaces may also be exempt from grounding requirements. If you are unsure whether your heating, ventilation, and air conditioning ducts need to be grounded, consult with a qualified electrician or heating, ventilation, and air conditioning professional. They can assess your specific situation and provide guidance based on local codes and regulations. Here are some common grounding practices used in heating, ventilation, and air conditioning systems. Grounding electrodes, such as ground rods and water pipes, provide a direct connection to the earth. These electrodes should be installed in accordance with code requirements and should have low resistance to ground. Grounding conductors, such as copper wires, are used to connect the ductwork to the grounding electrode or the equipment grounding conductor. These conductors should be sized appropriately for the fault current they are expected to carry. Grounding clamps and connectors are used to securely attach grounding conductors to the ductwork and other metal components. These clamps and connectors should be made of corrosion-resistant materials and should be properly installed to ensure a reliable connection. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Check for loose connections, corrosion, and damage to grounding conductors and clamps. If any issues are found, they should be addressed promptly to maintain the integrity of the grounding system. Grounding plays a vital role in ensuring the safety and reliability of heating, ventilation, and air conditioning systems. By providing a low impedance path for fault currents, grounding helps to protect against electrical shock and prevent equipment damage. Proper grounding also helps to reduce static electricity buildup and electromagnetic interference, improving system performance and air quality. When designing or installing a heating, ventilation, and air conditioning system, it is essential to consider the grounding requirements outlined in the National Electrical Code and International Building Code. Consulting with a qualified electrician or heating, ventilation, and air conditioning professional can help ensure that the grounding system is properly designed and installed to meet all applicable codes and standards. Grounding systems are designed to provide a safe path for electrical current in the event of a fault. This path should have low impedance to allow the current to flow quickly and trip a circuit breaker or fuse, disconnecting the power supply. The impedance of a grounding system is affected by several factors, including the length and size of the grounding conductors, the type of connections used, and the soil resistivity. Low impedance is essential for effective grounding. Higher impedance can impede the flow of fault current, increasing the risk of electrical shock or equipment damage. To ensure low impedance, grounding conductors should be as short and straight as possible, and connections should be clean and tight. Soil resistivity can also affect grounding impedance. In areas with high soil resistivity, such as rocky or sandy soil, it may be necessary to install additional grounding electrodes to reduce impedance. Several types of grounding electrodes are available, each with its own advantages and disadvantages. Ground rods are commonly used and are driven into the ground to provide a connection to earth. Water pipes can also be used as grounding electrodes, but only if they are made of metal and are in direct contact with the earth. Concrete encased electrodes, also known as UFA grounds, are installed in the concrete foundation of a building and provide a very effective grounding path. The National Electrical Code specifies the requirements for grounding electrodes, including their size, material, and installation depth. It is important to follow these requirements to ensure that the grounding system is effective and meets safety standards. The equipment grounding conductor provides a path for fault current to flow back to the source in the event of a ground fault. This conductor is typically a green or bare copper wire and is connected to the metal enclosures of electrical equipment such as motors, transformers, and panels. The equipment grounding conductor should be sized according to the size of the circuit conductors and should be installed in the same raceway or cable as the circuit conductors. It is important to ensure that the equipment grounding conductor is properly connected to all metal enclosures to provide a continuous ground path. Grounding and bonding are two distinct but related concepts. Grounding refers to connecting electrical equipment to the earth, while bonding refers to connecting metal parts together to create a continuous electrical path. Bonding is important to ensure that all metal parts are at the same potential, reducing the risk of electrical shock. The National Electrical Code requires that all metal parts that are likely to become energized be bonded together, including metal conduits, enclosures, and equipment frames. Bonding can be achieved using bonding jumpers, which are short lengths of wire that connect the metal parts together. Ground fault circuit interrupters are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. Ground fault circuit interrupters work by monitoring the current flowing in the circuit and comparing it to the current returning. If there is a difference of more than a few milliamperes, the ground fault circuit interrupter will trip, interrupting the circuit and preventing electrical shock. Ground fault circuit interrupters are required in many areas of the home, including bathrooms, kitchens, and outdoor locations. Surge protective devices are designed to protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage or destroy electronic devices. Voltage surges can be caused by lightning strikes, power grid switching, or other electrical disturbances. Surge protective devices work by diverting the surge current to ground, protecting the connected equipment. Surge protective devices are available in a variety of types, including whole-house surge protectors and point-of-view surge protectors. Whole-house surge protectors are installed at the electrical panel and protect the entire home from voltage surges. Point-of-view surge protectors are plugged into individual outlets and protect the equipment plugged into that outlet. Electrical codes and standards provide the requirements for grounding and bonding electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association and the Institute of Electrical and Electronics Engineers. Electrical codes and standards are updated regularly to reflect changes in technology and to improve safety. It is important to be familiar with the electrical codes and standards that apply to your area to ensure that your electrical system is safe and compliant. Proper grounding and bonding are essential for electrical safety. By providing a low impedance path for fault current, grounding and bonding help to protect people from electrical shock and prevent equipment damage. Regular inspection and maintenance of the grounding and bonding system are important to ensure that it is working properly. If you have any questions or concerns about grounding and bonding, consult with a qualified electrician. The National Electrical Code Article 250 provides comprehensive requirements for grounding and bonding electrical systems. This article covers topics such as grounding electrodes, grounding conductors, equipment grounding, and bonding of metal parts. Article 250 is an essential resource for electricians and other electrical professionals. Grounding electrode conductors are used to connect the grounding electrode to the electrical system. These conductors should be sized according to the size of the service entrance conductors and should be made of copper or other approved materials. Grounding electrode conductors should be protected from physical damage and should be installed in a neat and workmanlike manner. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Table 250.122 in the National Electrical Code provides the minimum size requirements for equipment grounding conductors. It is important to select the correct size equipment grounding conductor to ensure that it can safely carry the fault current. Bonding jumpers are used to connect metal parts together to create a continuous electrical path. These jumpers should be sized according to the size of the circuit conductors and should be made of copper or other approved materials. Bonding jumpers should be securely connected to the metal parts using approved connectors. The National Electrical Code requires that all metal water piping systems be bonded to the electrical system. This bonding is intended to prevent the water pipes from becoming energized in the event of a ground fault. The bonding connection should be made as close as possible to the point where the water pipe enters the building. The National Electrical Code requires that all metal gas piping systems be bonded to the electrical system. This bonding is intended to prevent the gas pipes from becoming energized in the event of a ground fault. The bonding connection should be made as close as possible to the point where the gas pipe enters the building. The National Electrical Code requires that all metal parts of swimming pools be bonded together to create a continuous electrical path. This bonding is intended to prevent electrical shock hazards in the pool area. The bonding connection should be made using copper conductors and should be securely connected to the metal parts. Regular inspection and testing of the grounding and bonding system are important to ensure that it is working properly. The grounding electrode system should be tested periodically to verify that it has low resistance to ground. The bonding connections should be inspected to ensure that they are tight and free of corrosion. If any problems are found, they should be corrected immediately. Grounding and bonding are complex topics, and it is important to consult with a qualified electrician if you have any questions or concerns. A qualified electrician can assess your electrical system and ensure that it is properly grounded and bonded. Proper grounding and bonding are essential for electrical safety and can help to protect you and your family from electrical shock hazards. Static electricity is an imbalance of electric charges within or on the surface of a material. Static electricity can build up on objects when they are rubbed together, such as when you walk across a carpet or when you brush your hair. When static electricity discharges, it can cause a spark or shock. Static electricity can be a nuisance, but it can also be dangerous in certain situations. For example, static electricity can ignite flammable materials or damage sensitive electronic equipment. Grounding can help to dissipate static electricity and prevent it from building up to dangerous levels. By providing a path for the static charge to flow to ground, grounding can reduce the risk of sparks and shocks. In areas where static electricity is a concern, such as computer rooms or manufacturing facilities, special grounding techniques may be used to minimize the buildup of static charge. These techniques may include the use of static dissipative materials, grounding mats, and air ionizers. Electromagnetic interference is a disturbance that affects an electrical circuit due to either electromagnetic induction or electromagnetic radiation emitted from an external source. Electromagnetic interference can cause a variety of problems, including data loss, equipment malfunction, and communication disruptions. Grounding can help to reduce electromagnetic interference by providing a low impedance path for the interfering signals to flow to ground. By diverting the interfering signals away from sensitive equipment, grounding can improve the performance and reliability of electrical systems. In areas where electromagnetic interference is a concern, such as hospitals or research laboratories, special shielding techniques may be used to further reduce the effects of electromagnetic interference. These techniques may include the use of shielded cables, shielded enclosures, and electromagnetic interference filters. Electrical safety is a critical concern in all electrical systems. Proper grounding and bonding are essential for electrical safety and can help to protect people from electrical shock hazards. Regular inspection and maintenance of the grounding and bonding system are important to ensure that it is working properly. If you have any questions or concerns about electrical safety, consult with a qualified electrician. A qualified electrician can assess your electrical system and ensure that it is safe and compliant with all applicable codes and standards. Electrical codes and standards are constantly evolving, and it is important to stay up to date on the latest requirements. By following the electrical codes and standards, you can help to ensure that your electrical system is safe and reliable. Grounding is important for heating, ventilation, and air conditioning systems because it prevents electrical shock by providing a path for stray electrical current to safely flow to the ground. Without proper grounding, the metal parts of the heating, ventilation, and air conditioning system can become energized, posing a shock hazard to anyone who comes into contact with them. Additionally, grounding can also help to protect the heating, ventilation, and air conditioning system from damage caused by electrical surges and lightning strikes. Static electricity can build up in heating, ventilation, and air conditioning ducts due to the friction of air moving through them. This static electricity can attract dust and other particles, which can reduce the efficiency of the heating, ventilation, and air conditioning system and can also be a fire hazard. Grounding the heating, ventilation, and air conditioning ducts can help to dissipate the static electricity and prevent it from building up to dangerous levels. Electromagnetic interference can interfere with the operation of electronic equipment. Grounding can help to reduce electromagnetic interference by providing a low impedance path for the interfering signals to flow to ground. This can improve the performance and reliability of the heating, ventilation, and air conditioning system and other electronic equipment in the building. The National Electrical Code requires that all metal parts of heating, ventilation, and air conditioning systems be grounded. This includes the metal ducts, the metal casing of the air handler, and the metal casing of the condensing unit. The grounding conductor must be sized according to the size of the circuit conductors that supply power to the heating, ventilation, and air conditioning system. The grounding conductor must be connected to a grounding electrode, such as a ground rod or a metal water pipe that is in contact with the earth for at least 10 feet. The International Building Code also requires that all metal parts of heating, ventilation, and air conditioning systems be grounded. The requirements in the International Building Code are similar to the requirements in the National Electrical Code. Homeowners should not attempt to ground their heating, ventilation, and air conditioning systems themselves. This work should be done by a qualified electrician who is familiar with the National Electrical Code and the International Building Code. A qualified electrician will be able to properly size the grounding conductor connected to a grounding electrode and ensure that the heating, ventilation, and air conditioning system is properly grounded. There are a few exceptions to the requirement that all metal parts of heating, ventilation, and air conditioning systems be grounded. For example, heating, ventilation, and air conditioning systems that are installed in dwelling units are not required to be grounded if they are supplied by a branch circuit that is protected by a ground fault circuit interrupter. However, it is still good practice to ground all metal parts of heating, ventilation, and air conditioning systems, even if it is not required by code. Grounding is an important safety measure that can help to protect people from electrical shock and to protect the heating, ventilation, and air conditioning system from damage. Proper grounding of heating, ventilation, and air conditioning systems is crucial for safety, static dissipation, and electromagnetic interference reduction. Always consult with a qualified electrician to ensure that your heating, ventilation, and air conditioning system is properly grounded and meets all applicable codes and standards.